Good morning. I'm Jim Barrowman. I'm going to be speaking this morning about model rocket stability, as well as talking a little bit about the equations for finding the center of pressure, which is a key component of stability. I would ask you to use the Q&A column over on your communication side of your display for any questions that you might want to submit. My plan is to work at the end to get through the questions, give you answers to those rather than in real time. But you never know. It depends on the nature of things. I'm mostly going to deal with concepts of stability and what try to lead to some understanding of why stability is important and what key are the key components to rocket stability. But I will touch on a little bit on the equations with some interesting insights as to some fortunate occurrences as I derive those equations. But as a matter of fact, I'm going to start with an equation. It's a key equation. It tells you why we even care about stability. I mean, it's very important, of course, because a stable rocket is a safe rocket, and a safe rocket is predictable. You know, you have a decent idea of where it's going to go. And most important of all, and finally, in addition to safety, is performance. A stable rocket, you know that it's going to be going in the right direction, and you know that it's going to have the best performance you could ask for. But there is a caveat, and I'll talk about that later. So stability is the kind of thing that we deal with in life all the time. We like our friends to be stable. We like our whole environment to be stable if at all possible. And certainly we want our rockets to be stable. Now, stability is in general concept, is the tendency to return to an original or a neutral position when something has been displaced from either going in the right direction or from sitting still. A good example of that is a ball in a bowl. You put a ball in a bowl and you pull it up to one side, and it's going to roll back and forth until it comes back down to the middle of the bowl. On the other hand, if you turn that bowl over and you sit the ball carefully on top and it gets displaced, it's going to roll off and bounce away, and that's a not stable situation at all. So that's a key concept of stability. You're either stable or you're unstable. There is such a thing as neutral stability. That is, if you displace something, it just kind of stays there, and that's if it's on a nice flat and level plane. That ball will just roll over and stay right there. So you get an initial idea of the importance of stability, but this isn't a rocket. Well, let's talk about rockets. For a rocket, that means that a rocket is, as it flies through the air, if it gets displaced by something, who knows, a wind gust or what have you, that it's going to work its way back to a minimum angle with the airflow. So that angle between the airflow and the rocket is typically called an angle of attack, and I'll talk more about that later. Of course, an unstable rocket, you don't know where it's going to go, and it's going to flop around all over the place. And as you can imagine, that's not a good situation. Neutrally stable for a rocket would be, well, you move it out of a zero angle of attack, and it stays there pretty much at that same angle of attack. That doesn't happen very often, if ever. So that gives you an idea when we talk about stability, what we mean and what it looks like if you're flying along with the rocket. On the other hand, if you're watching it as we usually do, this gives you some idea of a picture of what different forms of stability look like. A good stable rocket might wiggle a little bit, but it'll be flying up in the direction you aimed it. Unstable, Katie bar the door, watch out. It's going to hit you, and or it's going to hit something, and you probably don't want that. Finally, the neutrally stable rocket is still pretty wobbly and not very desirable. I thought I was sharing my screen. Somebody asked me to share the screen. Sorry about that. Okay, here it is. So again, the equation I was talking about. Thank you, Joyce, for piping up like that. I was all prepared, and then for some reason it didn't stay. But anyway, we're back. Stable equals safe equals predictable equals performance, and that's why it's important. Stability, not just for a rocket, for almost anything, follows that equation. And the stable and for some reason I lost the there it is. The stable motion in a bowl versus stable motion in an inverted bowl. And finally, the neutral stable motion. Again, this is good examples of what stability looks like, and something you could observe at home if you wish. And for a rocket, of course, then again, that means staying with the airflow. If it's disturbed, then it works its way back into a zero angle of attack with the airflow. Unstable, who knows? And neutrally stable, very rare. And of course, that's what it all looks like. You've seen it, I'm sure. Hopefully mostly stable, on a rare occasion, either unstable or neutrally stable. But obviously, stable is what we're looking for. Now, the key forces on a model rocket are twofold. There are translational forces on a rocket. These are the translational forces. They're the thrust, the weight, and the drag, typically. The drag is the key aerodynamic translational force because it's resisting your rocket flying as fast and as far as you'd like it to. And as you can see, if you're not flying straight up, then the weight is pulling it down, but they're all acting at the center of gravity of the rocket, represented by that little symbol in the middle of the rocket. The center of gravity is a very important concept in rocket stability and in stability and utilization of pretty much anything. That's where all the mass of the rocket appears to be concentrated. And typically, when you're doing a rocket simulation, or if you're trying to represent where the rocket's going, what you're doing is essentially simulating the center of gravity's motion. So the center of gravity is very special. It is the crucial concept and a very real thing. You can test the center of gravity of a rocket that's been built simply by hanging it on a string and seeing where it balances. And that means that all of the mass of the rocket, the weight as if it were, but actually the mass of the rocket is equally distributed on either sides of that. Of course, it's usually on the center line of a rocket, although not always. It depends on the details of additional parts of the rocket and how they're attached. but for the most part, they're very close to the center line of the rocket, the main axis. And again, all the translational forces act strictly through the center of gravity. On the other hand, the very key thing about the center of gravity that is important to stability is the fact that that rocket is going to rotate around the center of gravity at all times. This is a basic physical concept. It has to do with the distribution of the mass of the rocket being equally distributed around the center of gravity. To give you an idea, if you want to try this at home, an experiment, get yourself a stick. In the past, I've used a broom to demonstrate it because it's not exactly equally balanced. And you grab it at one end and try and rotate it. And you can see that it's very difficult to rotate, relatively speaking. You get it by the center of gravity, and it's much easier to rotate there. And that's exactly why it rotates around the center of gravity, because it's easiest for it to rotate about the place where the mass is equally distributed. So, but that brings us to the why that's important. The center, because it rotates around the center of gravity, the distribution of weight is equal all around the center of gravity, or the mass, but on aerodynamic forces, that's not the case. For aerodynamic forces, they are distributed by the shape of the rocket primarily. And when a rocket is at an angle of attack, it's shown here as alpha. The angle alpha is typically what we use to show an angle of attack. Those forces, although they're distributed, as you see on the left, they tend to act through the center of pressure. And that's why we talk about the center of pressure, because that, as with mass being equally distributed around the center of gravity, the aerodynamic forces are equally distributed around the center of pressure. And so those two key points on a rocket's center line are what we are concerned about as we look at stability of a rocket. Now, the difference between the center of gravity and the center of pressure induce a moment, that is, a force acting at a distance around the center of gravity. So this is an aerodynamic moment that is caused when the rocket is flying at an angle of attack. That aerodynamic moment is exactly the thing that creates either stability or instability in a rocket. So you have translational forces on a rocket, and then your aerodynamic forces are rotational. They tend to rotate the rocket, just like you would rotate your front wheel on a bicycle, or when you deal with moments all the time, opening doors. When you have a knob on the door you turn, you're creating a small moment that moves back the latch. So moments are a very important concept to the dynamics of anything, and particularly for a rocket. And in this case, we deal with aerodynamic moments. The aerodynamic moment, again, depends on the relative locations of the center of gravity and the center of pressure. And I think it's well understood by most folks that the stable rocket has the center of pressure behind the center of gravity as a rocket is flying. If the center of pressure is ahead of that rocket, it will the air forces will tend to rotate it further, and of course everything changes as you move the center of gravity. Those aerodynamic forces change quite a bit, and it can push a rocket anywhere and everywhere. So you definitely want that center of pressure to be behind the center of gravity. So the normal force acting, the aerodynamic normal force, shown here as N, is acting behind the center of gravity and pushing it back into the airflow and making it fly in a stable fashion. Now, I need to stop for a moment and give you that caveat. Yeah, you want your rocket to be stable, but there's such a thing as too much stability, and I can't emphasize that enough. Typically, a adequate stability is about 1 body diameter between the center of gravity and the center of pressure. That gives you enough margin. It's called the static margin, that distance between the center of gravity and the center of pressure. The margin to see that your rocket will be stable under pretty much all circumstances. You start getting it smaller than that, and things can happen if you get, say, a wind gust that blows it into a situation where the center of pressure has moved close to or ahead of the center of gravity, then it's become unstable. So you want that margin, that static margin, to make sure that your rocket will remain stable. On the other hand, if you have too much static margin, it becomes very sensitive to wind disturbances in particular. And when it does that, it will tend to weathercock much more quickly than if it's less stable or closer, has a tighter stability margin. So you want to be stable, but you really don't want to be too stable. And that therein lies the key to designing a successful rocket from a competitive standpoint, in that you want the maximum performance out of your rocket, and that means to minimize the response to winds and making sure that it flies as straight and straight up as possible. Now, there are a number of ways to determine a model rocket stability. Excuse me, while I was checking on some of the questions, just to see if there's anything that I need to deal with right now. There is a question, Alberto de la Iglesia asked, well, where does the 1 body diameter margin of stability come from? It doesn't come from anything, just experience. I mean, it's not, we understand from experience that 1 body diameter is about the right thing. It's something that's easy to remember, and it's but there's nothing magic about it. It's one of those experience factors that allow you to work with a lot of different things, including rocketry, that are not necessarily have any kind of mathematical derivation associated with them. It's just, if it's smaller than that, if it's much smaller than that, like I said, there's always a chance, because the center of gravity, or center of pressure, of course, the center of gravity is moving also as your rocket expends propellant, but the center of pressure definitely moves as the angle of attack increases. And it will, if it gets too far off of zero angle of attack, can really go to a negative stability situation, an unstable situation. So it's a margin. It's not magic. It's just giving you enough margin to assure that you have a stable rocket. Now, of course, for rockets that are already built, you can always do a swing test, so you can be sure that it's stable. That is it's almost too late because you've already built the rocket, and you should try and know your stability before you get to that point. It doesn't hurt to test it and make sure that it is stable. Nature has given us, or the situation with rockets in general and with model rockets in particular, has given us a nice situation, because as the rocket engine, which is at the back of the rocket, depletes its propellant, the center of gravity tends to move forward. So you tend to get an increasing center of an increasing static margin. So that's a good thing. On the other hand, the center of pressure can change mostly with angle of attack, and you want to make sure that angle of attack stays low, and therefore you have a center of pressure that remains behind the center of gravity. Now, for unbuilt designs, of course, getting the center of gravity, there's lots of ways to do that. Basically, before you build your rocket, it's a case of knowing the weight of all the various components of your rocket, and then summing up the contributions of those masses to the center of gravity, and dividing by the total mass. That's the total sum of the masses. And of course, that's the original concept of moments, because each of those design components have their own center of gravity, and each of those center of gravities have a distance from the combined center of gravity. And so you can pick it out analytically in that fashion. And there's a lot of all the design programs, the various simulation programs, have the capability to help you do that. Determining the center of pressure is a little bit trickier. Before you actually fly or have a rocket to do it with, the most popular for a long time has been the cardboard cutout method. That provides a very conservative answer. It's an answer that basically allows you to see where the center of pressure is, the center of pressure, if the rocket is flying normal or sideways, normal to the airflow or sideways. So if the rocket's flying sideways, that's where your center of pressure is. So that you can see very quickly when you compare the center of pressure by the cardboard cutout method and by other methods that give you the center of pressure near zero angle of attack, that's quite a difference. The center of pressure actually moves a bit forward compared to where it is at zero angle of attack. And that's why, of course, a rocket can go unstable because of that motion of the center of pressure. Now, I did put together some aerodynamic equations early in my career, and those are probably the best way to determine the center of pressure. That is available in the Handbook of Model Rocketry. They're generally available on the web. Usually you can just Google center of pressure or rocket center of pressure and get a number of different things. Particularly, there's a design program such as RockSim and Open Rocket and others that do include buried in them the equations for the center of pressure. And I encourage you to use those design programs, because they can really make it easy and make it direct process of getting that. So in getting those aerodynamic center of pressure, CP equations, I did that as a NASA engineer working with sounding rockets. sounding rockets and model rockets are both aerodynamically stabilized. There's one sounding rocket. Sounding rockets, by the way, are rockets that, like our model rockets, don't go into orbit, but they fly up quite high, and in many cases into the space environment, but they don't have the energy to take them all the way into orbit, and typically you need very careful thrust vector control to get to get to orbit, because you need to orient your thrust in the proper direction. And so there's a similarity, and therefore I could go ahead and use that similarity to apply those equations in a simplified form to model rockets. The work is based on a lot of engineering and research that was done by NACA, the predecessor to NASA. They were primarily concerned with aircraft, but in many cases also rockets. So there was a lot of work done before NASA ever came to be that I was able to utilize. It never had really been pulled together in one place, and I actually put together a computer program that we used on a regular basis to analyze our sounding rockets. And I did some simplifications and made some careful assumptions, which I'm going to talk about in a second, that allowed us to apply those same equations without using a computer. You can actually do those calculations by hand. So we'll see in a minute what that was all about. The simplifying assumptions, many of them actually, these assumptions, there's a couple of them that are crucial to model rocketry, but most of them are the same assumptions I would make in deriving the equations for sounding rockets or full-size rockets, and actually could be used for regular launch vehicles too, except that launch vehicles have a very specific capability, and that is their thrust vector control and stability control that allows them to actually control their stability without fins, and therefore less responsive to wind and aerodynamic aspects. But in our case, we're dealing with aerodynamics strictly, although there have been a few control systems built for model rockets. But in general, we're dealing with an aerodynamically stable rocket. One important thing is that the rocket is a rigid body. This makes the super rock folks, the folks that fly rockets that are many, many, many times longer than they are in diameter. That's a tough assumption to meet with a super rock. And therefore, what does that say? Well, you can still use the equations, but you have to have a lot more static margin to be sure that as the rocket flies, it doesn't go unstable. An actually symmetric rocket, that is a rocket that looks the same pretty much from all directions. Again, you can have 3 fins or 4 fins or 6 fins, but in general, you want to have those fins spaced equally around the rocket. And the rocket itself is typically the cross-sectional the cross-section of a rocket body is typically a circle. It's actually symmetric. It's symmetric around its main axis, so that you're not getting a lot of bumps and actions on one side or the other. For example, the space shuttle is not an actually symmetric rocket. And I'm sure we've seen lots of not actually symmetric rockets. And of course, I think you've got to use a lot of careful judgment as to how far away from truly actually symmetric you can go. You put a launch lug on the side, that's probably not a big deal. You have tabs on the side for a launch guidance, that's probably not a big deal. You can probably go pretty far without violating that assumption badly enough. What it means is, as I said about the rigid body, the further away from actually symmetric you get, the larger static margin you should be using. Now, the third one is the flow over the rocket is potential flow. That's an aerodynamic concept. It means that there's no turbulence in the flow, that is, it's smooth flow. There's no vortices. They're flowing over the rocket, at least very small ones. And the friction, of course. And again, those are assumptions that are used because even though they're not strictly true, but it's close enough that you can go ahead and work the center of pressure, or you can do aerodynamic analysis as long as the flow is potential, because you're using what can I say? You're using the analysis equations that are derived from more detailed aerodynamic factors, but they are derivative and not exact to what's going on aerodynamically. The other key assumption is the fins are thin flat plates. Again, that's just so you can simplify the equations to the point where they're usable without a computer. A lot of aerodynamic analysis is done on computer in detail, and you can analyze all kinds of shapes and sizes, but as a rule, we don't have access to that kind of capability. When I was deriving these equations, my goal was to make it such that a junior high school student could utilize these equations by manual computation, or with of course, when I first derived them, we didn't have calculators other than big, chunky calculators that sat on a desk. We didn't have personal calculators you could carry around and that were programmable. The thin flat plate is a conservative assumption, by the way. That's if they're not thin, if they're not flat plates, that is, if they have a cross section that's more like a wing, that doesn't hurt anything. They actually are better. They provide more lift and more stability if they're not flat plates. So that's why it's a conservative assumption, and there's no problem with flying things that are not exactly flat plates. Those flat plates, those fins, should have no cant. That is, they should be aligned with the center line of the rocket. That is not strictly necessary. That is, you could have slight cants on your fins so the rockets will spin because of the cants causing the rockets, allowing the rockets and causing the rockets to spin. But you don't want to go too far with the cant, and of course you'd like them to be equal, or you run into another kind of stability problem, which is a dynamic stability problem. I'm not going to talk about that today, but most rockets don't have that problem. It's really only becomes a problem when the spin rate is about the same as the lateral frequency rate. In other words, as your rocket wobbles back and forth, it has a natural frequency. You don't want that spin rate to be near the natural frequency of the rocket, or it could go unstable dynamically. The angle of attack is near zero, is a very important one. Near zero, again, it's kind of like what we talked about earlier with the concern about the static margin itself. That's not it's not an absolutely critical thing, but it's important enough that you want to keep it less than or equal to 10 degrees. You won't know until you fly it, of course, but if you keep that static margin, you've got a very good chance of staying with under 10 degrees angle of attack. The flow is steady state, and that's also part of the potential flow situation. It means that it's not, again, it's not turbulent. It's not all of a sudden, right off the launch rod, or right if you didn't have a launch rod, right off the ignition point. You're not at steady state because you haven't established the flow in a smooth manner over the rocket. And of course, everything assumes that the rocket is already flying smoothly through the air. That's why we use launch rods. The flow is subsonic, and this is key for model rocketry, of course. The work I did with sounding rockets took us all the way to supersonic, because sounding rockets can fly as high as Mach 5, 6, 7, as high as 10. So the equations or the analyses that I pulled together for sounding rockets went through the speed of sound into the supersonic region. Subsonic, you're talking about Mach 9 or lower. It's very hard to get anywhere near sonic with a model rocket. People have done it, as I understand. I've never witnessed it myself. Not sure how one can be certain that they have reached the speed of sound with a model rocket, but I heard that there are those that have claimed it, and okay, that's good for them, but they better be careful with their static margin if they're analyzing it as a subsonic rocket and it goes supersonic, or it goes at least close to the speed of sound. The center of pressure is going to change, and there again it moves forward. So it gets smaller, and therefore you should have more static margin. So those were the assumptions. I'm not going to spend a lot of time on the equations themselves. The equations are generally available, as I said, online. If nowhere else, they're available in the Handbook of Model Rocketry. I would recommend you take a look there. If you assume that you either get it out of the library, or you have a copy. The other places, of course, I wrote some technical reports for Centuri, which have been adopted by Estes, and they have those technical reports, which include both the equations and graphs that you can use to apply the equations. So they are available that way. I saw earlier that George Flynn had asked the question about the availability of the equations, and I for one refer to those reports all the time. I really don't know of any other place other than those than either the Handbook of Model Rocketry or those technical reports, which are typically available on the web if you search well enough. And a lot of people have put them on in their own form as well, but not as formal reports. So let's look at one part of the equations, and that's for the nose center of pressure. The nose center of pressure, I've chosen that because it turns out to be fairly simple. I'm showing you a little bit of derivative equations so that you have a sense of what it takes. X bar, of course, if you look at the top equation, is the center of pressure from the nose tip, and that is essentially the d, or the distance, and ultimately it becomes the diameter of the rocket, because we just use that as a reference number, times the cm alpha, that is the non-dimensional aerodynamic moment, divided by the non-dimensional aerodynamic force. And those aerodynamic coefficients, they're called aerodynamic coefficients, are actually, they take into account the velocity and the density of the air. Essentially, they are the force divided by the dynamic pressure, which is a function of the density of the air and the velocity of the air over the rocket. So we use those coefficients because you take that out of the picture and you're dealing only with the shape of the rocket when you're dealing with those aerodynamic coefficients. So you're not dealing with the actual forces, you're dealing with the part of those forces which are dependent on the shape of the rocket. The aerodynamic moment is the integral, that is the summing up of all the aerodynamic forces over the length of the rocket. And similarly, the normal force is summed up in exactly the same face as the Cn alpha. Cm alpha is Cm alpha, the moment coefficient, is a little bit more complicated because you're summing it up by x, that is as a function of the length over the rocket. So things change dramatically as you do that, even on a simple shape like a nose cone. And by the way, that's where the key assumption of the nose coming to a point, or not really a point, but that the nose comes to a zero area at the very beginning. So it could be rounded, that is like a spherical nose or an elliptical nose. It could be rounded, and even with the most conical noses, the very tip of the nose is slightly rounded. They're not going to cause blood if they poke you. So they all actually end up with a zero area at the tip, and that's the real meaning of that coming to a point. So using those assumptions, using some calculus, first of all, the Cn alpha is really just a function of the area, and that can be added up. There's some simple numbers for the cone. Well, it all adds up. They all end up with the same number, is what I should say. And that's simply because they're actually symmetric. They're all actually symmetric. And so it ends up with a Cn alpha of 2. And if you have access to my the thesis that I wrote for my master's degree when I derived these equations. You can see how that's derived, but it's not really that complex compared to the what it took to get to the volume, which is the same which is the key component of the center of pressure or CM alpha equations. So, after all that derivation and stuff, the center of pressure is a function of the volume divided by the base area of a nose cone. The length of the nose cone minus, because it's from the tip, not from the base. So the center of pressure is the length minus the volume divided by the base area. And fortunately, that's a fairly simple thing. You can determine the volume of a sphere. You can determine the volume of a paraboloid, that is, of an elliptical, not a paraboloid, but an elliptical nose cone. And actually, you can determine the volume of a paraboloid, a parabolic nose cone. Turns out for a cone, the center of pressure is about 2/3 the length. It's 2/3 the length. For a sphere or an ellipsoid, it's a little bit more complicated. It's pi over 6 times the length times the diameter squared. That's the volume of either an elliptical or a spherical nose cone. A parabola turns out to be simple again, relatives, and not simple to derive, but simple to use, and that is it's 1/2 the length of the nose cone. So it's the numbers turn out to be fairly straightforward once you go to specific shapes. You get much more complicated shape than that, and it really gets quite complicated. The one shape that really interests me, of course, in flying model rockets is people ask, well, what about an ogive? A spherical ogive is essentially an arc of a sphere that's been actually rotated. So you just take an arc of a sphere that has been rotated, has been cut off of or arc of a circle that's been cut off of the circle and then rotated such that it forms the nose cone, which we call an ogive. And that particular beast ended up with a formula for the center of pressure, which was a monster. You can see this at the top of the next slide. It is not something you want to tackle by hand. And so I got lucky in the sense that when I went and computed it, and I said, well, now I'm going to have to create a graph so that people can use this without having to do that crazy formula. But as it turned out, that graph looks mighty like a straight line, as you can see down below. And in fact, you can end up using the center of pressure of an ogive, tangent ogive. It's a tangent ogive because the base of the rocket, the base of the nose cone, is is derived from the radius of a circle. So you take that arc that comes from a radius of the circle and extend it down to the tip of the nose, however far you want to go. Ultimately, it becomes a semicircle, or you'd be dealing with a hemisphere, but just partially done, say only about 15 degrees or so, and you rotate that down, and then you rotate that segment of the circle. That's how you create an ogive shape for a nose cone. And that shape ends up with ultimately a fairly simple thing. The simple number to go, so the x is 0.466 the length of the nose cone. And so that's just a bit of luck that in the derivation of the equations, I was able to not have to go through some crazy graphic, although I did use graphs eventually. So these equations are pretty well proven. We've proven them through sounding rocket wind tunnel analysis, and I flew a number of models before I ever showed anybody the equations and showed that they flew well. And since then, it's been over 50 years and thousands of stable model rockets. I've shown that these things are accurate and will do the job for you. So as you work stability, remember that first equation. You want it stable so it's safe, most of all. Then it's predictable and it'll do the performance. And you really want to know it before you fly it. Let me answer some of the questions that have come out. And let's see. Steve, I think I answered your question to the best of my ability. I can't say that there isn't. I mean, the open source library that I know of is the web itself. CP diagrams often show a bump at the base of the nose cone. I'm not sure what diagrams you're talking about. I'm not sure exactly what you're saying, Terrell, what you're asking. CP diagrams. Again, I'm not sure exactly what you're talking about. There is as you go, if you go tangentially, if your nose cone comes in so that it comes in so that the base of the nose is tangent to the body tube, then it should be a smooth flow of smooth. The air pressure stays pretty smooth there. There's no bump. However, if there's a discontinuity, like with a cone has a discontinuity, because unlike an ogive and like a spherical nose cone, it doesn't come in smoothly and is tangent to the body tube. If you visualize that when you draw it, and actually there's a bump there. That's probably why you see a bump in the Air Force diagram, and I think that's what you may be talking about. From Robert Willen, we're building a small amount of spin. No, it doesn't make it more stable necessarily, and you can't rely on it to that extent. A small amount of spin, what it does is if there are misalignments in the rocket, either in the thrust or in parts of the body, it tends to even those out by spinning the rocket slightly. It doesn't hurt to spin it a little bit, but it doesn't help it the stability. It just evens out any asymmetries, so that it will tend to fly more straight up than if you didn't spin it. The next question from Rebecca is, what are some steps that would have to be done to calculate the stability of a rocket for supersonic, hypersonic flow? To do that, you have to do numerical integration of the flow field. It's quite complex. It's actually done for aircraft as well as rockets. It takes a good-sized computer. It takes a number of different kinds of codes have been developed to do that. And it's really a function of what you're looking to do, what kind of vehicle you're dealing with. I wouldn't worry too much about it for model rocketry. The folks at Wallops now have the computer program that I developed for that includes supersonic and hypersonic flow. Again, the approach that I used was more derivative, because it doesn't do individual flow field analysis, because of the symmetry of rockets, you don't absolutely have to. But for aircraft, you definitely have, and anything that's not symmetric, you have to do that. Well, my time is about up. I'll try and answer the next two if you're willing to stick with me, and then we'll be done. Robin? The graphs of TR33 are simply the equations put out in graph form. I guess I'm not sure what it was about the graphs you didn't understand, Robin. The idea was that you're able to use the information about the shape of the rocket, either the nose cone shape or the fin shapes, coupled with those graphs in order to determine your center of pressure. And I guess I'm kind of at a loss to answer any more than that. They're simply graphic forms of the equations, and by putting in the parameters that are as part of the graphs, they allow you to calculate the forces and moments that you need to compute the center of pressure. Let's see. For squat rockets, Kurt Gunther, apparently the rule of thumb for one body, rather conservative. On squat rockets, well, again, the whole thing is just being careful to have enough of a static margin. If for short rockets, you're probably more sensitive to that but on the other hand, it's harder to move that center of pressure around because you don't have either fin distance, although you can stick the fins out a lot further and what have you. You just have to, I would say, just use that same rule of thumb, and as long as you have that one diameter, you should be okay. For Mark, yeah, the Gemini Titan needs either fins, some kind of a plastic fin stabilization. A lot of people just use clear plastic fins so you don't see them. Don't know what else you can do. You get to the point where you have to put so much weight in the nose, it's not good. So I'm not sure what to say. You have to have some fins. They are aerodynamically stabilized. If you don't have something, they're gonna not be stable. The conclusion pages. I don't remember exactly. Will, I'm sorry, I don't know what you're talking about in terms of the conclusion pages. All I did was recount the center of pressure equations, and that's all I can say. But I think it's better to use the technical reports simply because they're laid out without all the derivation. So with that, I'm done. Thanks. Enjoy the rest of the convention.